Alright, so this will be the last video for section 3. This is kind of like the last lecture for the first week here in the summer. Things might get broken up a little differently in the fall, but definitely the last of this section. So we're going to talk about structure of atoms and subatomic particles. And so these go hand in hand. So subatomic particles are the pieces that atoms are made out of. So it turns out that everything's made out of atoms. You can break it in atoms, and then those atoms can be broken into even smaller pieces. So it's like the Legos are made out of Legos. And then it turns out that those subatomic particles are made out of pieces. It just keeps going all the way down. Like those are made out of pieces, which are made out of pieces. But the nice thing is, as a chemist, if it's smaller than a subatomic particle, it's smaller than an electron, it's not my problem. So, these things like muons and gluons and like the Higgs boson, known as the God particle, which people take to mean the wrong thing because they're being polite. What it really is the goddamn particle. Like, we can't find this goddamn particle. Like, that's the name. I'm quoting a name. You can't get me in trouble. That's science. And that's true. That's true. It just kept coming up over and over again, and they just couldn't physically observe it. But it was necessary theoretically. They had to build the Higgs boson collider, or the Higgs hadron collider, excuse me. The Large Hadron Collider. Which is a massive international collaboration, like 3,000 scientists working together on this thing. When a paper gets published, there's I don't know how many pages of just the names of the authors because they all get credit for it. And all of that was necessary to find that one little particle, the God particle, which, as you know now, stands for something else. So, it's nice that that's not my problem. Like, if I want to see electrons, I just look at lightning, and there they are. If I want to see nuclei, yeah, with the naked eye, not really possible, but, there's tricks to the trade. We have instrumentation that can do that. We can observe them indirectly. Alright, so, structure of atoms. We'll start there. And I'm going to start with what I call the fried egg model. Not Friday, fried egg. I have to be very careful to pronounce that. And so we have kind of two pieces. We have a nucleus, and then we have an electron cloud. This is the most basic model. We're going to build up from this. You probably see why I call it the fried egg model. And that's my own name for it. I take all the credit for this. One of my great teaching accomplishments is I decided on a way to make an atom look like a fried egg. Now, this isn't really to scale, and we'll talk about that. These pieces, obviously, this isn't the size of an atom, but also, this nucleus is way oversized for this electron cloud. It should be much smaller. But, we have these subatomic particles, alright? So the nucleus is in the middle, and it contains what we call protons and neutrons. Don't ever try to get neutrons on your side in an argument. They're indifferent to everything. Very neutral. And then we have, you'll never guess what's in the electron cloud. It's not clouds, I'll give you a hint. So, and then the electron cloud contains electrons. And there's actually some organization to how the electrons are in there, and we'll get into that later. So there's the two pieces to the atom. Like this is an atom right here. Okay. Now we can get a little bit more specific, which we'll get into later. But first, let's talk about what these pieces are. We got protons, neutrons, and electrons. These are the subatomic particles. So there's three kinds. And so we've got protons, neutrons, and electrons. And there's a couple properties that we're going to care about. First one is their electric charge, and the second one is their mass. That is all we care about. And so all of these electrons are in the cloud, and they're orbiting the nucleus. And the nucleus is where these two are. Right? That's what it contains. And so protons have a positive charge. electrons have a negative charge. And we can think of this also, you know, it's like a +1 and a -1. So they're equal and they're opposite charges of equal magnitude. So +1, -1. And neutrons have 0 charge because they're neutral. And protons have a mass of about 1 AMU, which stands for atomic mass unit. It's like a 1. Neutrons are 1 AMU. And electrons are 5 times 10 to the -4 AMU. Now typically atoms are going to have about the same number of protons, neutrons, and electrons. Protons and neutrons can flip around a little bit, but an elemental neutrally charged atom will have as many protons as electrons. And so there's a couple things here. Now the first is, in general, we have these two pieces of the nucleus. This piece has essentially all the mass. This is essentially an insignificant... I hope you guys aren't hearing my super squeaky chair, by the way. I'm going to sit forward on it so the back stops doing that. Alright, so this is like an insignificantly small. This is very small. So it's, you know, it's essentially 0. It has volume, it has mass, it is a form of matter, but compared, it's like 1/20,000th. Or maybe it's 2,000th. Yeah, it's like 1/2000th of these guys. And there's no atom that has 2,000 electrons on it. So it's just not going to come into play. So it's essentially 0. So what that means is the nucleus contains pretty much all the mass in the atom. The electron cloud has a little bit, but it's like a rounding error. You know, it's like how many, you know, you look at Bill Gates' bank account, it's like, well, you know, yeah, it's $50 billion and how many cents? Yeah, no one cares. So it's, you know, it's a rounding error. And so there's essentially no mass in the electron cloud compared to the nucleus. On the flip side, you've got these two properties of matter, right? So it's got to have mass. Mass is in the nucleus. But it's also got to have volume. Now the electron cloud takes care of the other half of the equation. The electron cloud is the majority of the volume. So this is our volume. And this is our mass. So there's a little tiny nucleus. Like I drew this way out of scale. If I drew a dot with an electron cloud this size, that would be too large. I can't make a small enough dot to represent the nucleus with this pen. Not even if I use the little skinny end that I never use. That would still be too large. I mean, the nucleus is insignificantly small in volume compared to how much the electrons spread out around it. Like you've got this little... It's like if you got the world's luckiest avocado, and the pit was just like not there, and the whole thing was just avocado, right? Normally you go to the store and you play the avocado lottery, and you come out and you have an avocado like this size, and you cut it open, and somehow there's a pit in it that's like this size, like it's bigger than the avocado, and you're like, I just paid for an avocado I can't eat. But an atom is structured like the greatest avocado ever. It's all green and luscious, and you can't even see the pit. It's too small. And so that's how the atom is. The nucleus, it's very dense, it's very massive, it's really small, and then boom, there's an electron cloud all around it that takes up a ton of space. And so the electron cloud provides the volume, the nucleus provides the mass. There's kind of a division of labor there. Okay, so there's a couple different ways to talk about these atoms. There's a couple different terms we're going to introduce here. So we're going to circle back to the idea of elements, but we're also going to introduce ions and isotopes. So, elements are atoms with the same number of protons. So I'm going to abbreviate protons as P with a plus because they're positive charge. The word starts with a P. So, you know, for example, every element has a name. There's a periodic table of elements that will that's the key to this. We'll talk about that in the next section more. But just for example, you know, all atoms with one proton are hydrogen atoms. That's the name of the element. They're all the same element. That element is called hydrogen. If they have two protons, well, they're not hydrogen. And if you look at your periodic table, if you know how to read it already, you can see that they're helium. And so that's what elements are. So like the difference between gold and lead is the number of protons in the nucleus of those atoms. And so a gold bar has a bunch of atoms that all have the same number of protons. That makes them gold. That's what defines the nucleus. Okay? So, the other thing is the number of protons equals the number of electrons, which means that they have zero charge. Okay, keep that in mind. So hydrogen atoms are going to have one proton. They're also going to have one electron and have neutral charge. If the number of protons and electrons are not the same, so we can do that. We can move electrons around. We can take them away. We can add them on. We'll talk about trends with that with the next section. But when we do that, we get ions. So this is when the number of protons does not equal the number of electrons. So if we change number of protons in the nucleus, we get a different element. If we start changing the number of electrons around that, we get an ion. So every element can have, you know, what we call ionized atoms. We can change the number of electrons around the number of protons. Now the idea of changing number of protons, that's nuclear chemistry. It's actually really tricky. But if we look at like different atoms with different number of protons, we're getting different elements. But we can move electrons. They're really small. They're really easy to move. We're doing it right now. I'm using a laptop that's moving electrons through it to do all kinds of processing of my video and record it onto a hard drive where electrons are being flipped with a magnet. You know, this camera right here uses electrons to record color and motion and video and everything. And so yeah, electrons can be pushed around real easy. Remember that they're very light, so they move very quickly. We can do a lot with them. Protons are like stuck. They're like glued in the nucleus. Much harder to deal with. Okay, so what this means is charge does not equal zero. We have an uneven number of pluses and minuses. So in elements we might have 3 protons, 3 electrons. Well, that's plus 3 minus 3. We add them up, we get 0. But maybe now we have 3 and 2. Well, now we have a overall charge of plus 1. One of these pluses isn't canceled out. So if we have a overall positive charge, number of protons is greater than number of electrons, we call this a cation. Because we can have two situations, right? Like we can have more protons than electrons. We get an overall positive charge. We have more pluses than minuses. We get a cation. Why do we call it a cation? Because cats secretly rule the world. The internet has taught us this. They took over the internet. And now it's all over. My dogs live in fear every day. And so it's positive cation. Alright? Even though cats are like incredibly negative. My wife had a cat that she got as a kitten, and it lived 20 hateful years of existence. For sport, it would hop up onto like a dresser, and it would wait till you were looking at it. It would just put its paw out. You know, there'd be something on the dresser, and it would go, you know, tap it to get your attention. And as soon as you looked over, look at you, and it would knock it off the dresser, fall all the way to the floor, and then the cat would run away. Like that was its hobby. It was that, and then like controlling the staircase. It would just lay on the stairs and control it. Like no other cats could go through the staircase. It was just a little bundle of hate. And its final act of revenge, it made it to like 20 years of age, and then it started dying on my birthday. Like, that's what the cat did. And it knew what it was doing. And I still miss her to this day. Anyway, if we have an overall negative charge, my dogs are just too cheery. They're too happy. They see me and they're like, oh, the cat would seem to be like, oh, you came back. There's just something refreshing about that, you know? So now it's the opposite situation. So now the number of protons is less than the number of neutrons. Because you remember these little brackets, they're little hungry alligators. They bite, they're big game hunters. They go after what's bigger. They bite the big, big prey. So now the electrons are the big prey, alligator bites it. You'll never forget how to read these again. You're welcome. I'm 35 years old. I still use that technique. Never fails. Now what we call these are anions. Because, sounds like onion, so it's a negative. So we can have an overall positive charge, overall negative charge. So if we change number, if the number of protons are different element. If the electrons get out of whack with the protons, we get an ion. And then isotopes, it's a pretty straightforward idea. We're messing with protons, we're messing with electrons. Now we're going to mess with neutrons. But students get tripped up on this a lot, so just bear with me. So every single element has multiple isotopes. It's kind of like, think of elements as like flavors of ice cream. And so you can have chocolate ice cream, but there's different kinds of chocolate ice cream. You got chocolate, you got dark chocolate, you got German chocolate, you got white chocolate, like those are all chocolate ice creams. So, isotopes are like the different flavors within the flavors. You can also have like vanilla and French vanilla and, I don't know, super fake vanilla and so on and so forth. Cheap dollar store vanilla. The worst vanilla of them all, I assume. And so those different types of vanilla, that's isotopes. And so what that means is, so we're messing with number of neutrons. It doesn't change the charge, it doesn't change the element. It's just the only thing that changes, because they have no charge. It just messes with the total mass. And so you can have a atom of gold that's a little bit heavier or a little bit lighter than average as the number of neutrons in it change. And those are just different isotopes. And so there's generally, most elements, so we'll talk about this more with the periodic table, most elements have one isotope that is the most common. It could be 9,999 out of 10,000 are this type of isotope. But there are still other isotopes present. And they might not be stable, so they might not last long, but they're there. So be aware that every element has multiple isotopes, but typically there's one that just shows up more often than the others. So, these are atoms of the same element with different numbers of neutrons. So for example, we could have like carbon 14 and carbon 12. And so this guy, carbon 14, so we'll pit them against each other. Carbon 14 versus carbon 12. So carbon 14 has a total mass of 14 AMU, whereas carbon 12, and this is actually the most common isotope, almost all carbon is carbon 12, is 12 AMU. And we'll talk about this later, but they both have 6 protons. And so this guy has 6 neutrons, this guy has 8 neutrons. That's the only difference. Chemically, they're going to behave the same. This one will decay over time. It's using like carbon 14 dating, but it takes tens of thousands of years to notice it. Or not tens of thousands, it takes a couple thousand years to notice a change in the amount of carbon. Like half of it goes away every couple thousand years. So it's relatively stable, but this, carbon 12 is forever. They say diamond is forever. Well, it's made out of carbon 12 mostly, so carbon is forever. That's what we're looking at here. But for now, don't worry too much about the details with the numbers. We're going to talk about that more. Periodic table is going to be so key to this. Like, that's really the big piece that'll make this click. But just keep in mind that we've got protons, neutrons, and electrons. And the numbers of those can vary in atoms. Now, an element will always have the same number of protons and electrons, and it is defined by the number of protons. That's what makes an element an element. We can change the number of electrons around that nucleus and make it an ion. An element will have no charge, an ion will, and it can be positive or negative. And then within every element there's also a series of isotopes. So, there's also a carbon-13 that exists in the middle here. And there's a really unstable and unhappy carbon-11 that can show up. But typically there's one that's favored, and there's others that are around. And all it is a difference in neutrons. So like I said, it's like this is vanilla, and this is like French vanilla. They're both vanilla, but they're a little bit different. One's heavier than the other. There you go. Alright, and so the last thing we're going to talk about. Well, actually, no, that's it. Yeah, we'll go into more detail. We're going to build on that fried egg, but we really want the periodic table to do it. So this is where we'll leave it for now. This is the end of the first week. Congratulations. I hope you stick around. Hope you're not too sick of me already. I have clearly been alone. Well, my wife's here, so I've clearly been alone for too long in a little house with someone who is a little more social than me. So a little mismatch there. So maybe I just run these videos long to be by myself. Who knows? Anyway, feel free to do the same. Just watch them halftime. Just keep your headphones on. I'm studying. All right. But yeah, so that's the end of the section. Enjoy. As always, any questions, we've got the help forum in there, and I will reply to stuff if students aren't replying. I'm okay with you guys kind of helping each other out. Start of the second week, I will assign groups for answering group questions. I want to just make sure that everyone's done with the adds and drops before I do that, and you can kind of begin the regular process. First week will be a little bit different, but after that, all the sections are going to kind of run the same. So, well, actually, I think I have to do group discussion stuff week 1. I think there's group discussion things in these sections. I'll have to look. Like I said, it's the first time I taught this online, so I'm feeling it out a little bit. As always, any suggestions, let me know. Otherwise, see you next week. All right.